Or great. Okay. Welcome everybody to lecture 3. As a recap, over the last 2 lectures, we have seen how to use divide and conquer to speed up arithmetic. In the first lecture, we've seen faster integer multiplication, which by divide and conquer and the Karatsuba algorithm let us go from n squared to n to the log base 2 of 3. Okay. And then in the last lecture, we've seen how to speed up matrix multiplication via Strassen's algorithm that let us go from n cubed to n to the log base 2 of 7. Okay. Now we're gonna temporarily leave behind arithmetic, and today we're primarily going to talk on computational tasks on lists. We're going to specifically look at sorting and finding the median of a list. Okay, and we'll see how divide and conquer as a technique helps us get good algorithms for both. So that's the plan for today. All right, sorting. So, well, what is sorting? Hopefully that is reasonably familiar to you, but just in case it's not, the specification of the problem is as follows. The input to the problem is a list of n numbers, or really more generally anything on which you're able to assign a total order. Okay, and you want to output them in increasing or decreasing order according to the comparison operator you've defined on this list. Okay, but for now, just think about them as numbers. Okay, and there's like a million sorting algorithms out there that you may have seen. Today we want to specifically talk about one that arises through the thinking of so divide and conquer. And specifically we'll talk about an algorithm known as merge sort. Okay, and the intuition for merge sort is actually pretty straightforward. It's something that it's such a cute algorithm that if you were asked to, I don't know, just come up with a divide and conquer sorting algorithm, you could probably sort of come up this yourself, without ever really having seen it. Okay. Anyways, the algorithm has 3 steps. Remember that for divide and conquer, you have to somehow split your problem into smaller subproblems. So if you have a big list, why not split it into 2 smaller lists? Okay, so we're gonna split. The first step is to split the list into 2 halves. Okay, now this is a smaller input size. You go from n to n over 2. So how about we just recursively sort them? Okay, so we recursively sort each half. Okay, that's fine. That's just it's a recursive call to yourself, right? But now you have 2 sorted sublists consisting each of n over 2 elements. So we're going to have to somehow put them back together to obtain the final sorted list. So now we're going to merge the 2 sorted halves. And we could even leave, I mean, to some extent, these 3 steps are basically a precise specification of the problem, but of the algorithm. But just in case there is some doubt, let's fill in also the pseudocode. Okay, just to be more precise. So we define a recursive procedure called merge sort. It receives the n numbers to sort. Okay. Now, like all recursions, you do have to have an understanding of what to do in the base case. So in the base case, it's going to be when you're asking to sort a list that consists of a single element. That's pretty easy, right? You just return the element. Okay, there's nothing to do. Great. So you have a well-defined base case. Now, if we're not in the base case, that means n is greater than 1, and we have the opportunity to split the list into 2 halves, right? So what we're going to do is we're just going to take the first half and stick it into the first recursive call. So we put a1 ... up to an over 2. Okay, and then we're going to recursively sort the other half, which is an over 2 plus 1, all the way up to an. Again, we're recursively calling ourselves on an input is half the size. That's fine. It's well defined. And now we have each of these 2 recursive calls are going to return a sorted list. Let's call them SL and SR, for S left and S right. And then we're going to construct the final list S by merging the sorted list from the first recursive call and the sorted list from the second recursive call. Okay. So that is our merge procedure. Now, what does it mean to merge? So can anybody suggest what we might do to merge two sorted lists?
Well, if we know that the least element of the right thing is greater than the largest element of the left thing, we can just combine them. We don't have to do it. We don't have to do any element by element checking.
Right. We can. So let's say that we're talking of increasing order. So I can look at the leftmost element of both lists. So in this case, here's an example of two sorted lists. Let's say this top one is SL and this bottom one is SR, right? This is in order, that's in order. They're just not merged yet. I'm going to look at the leftmost element, and there's going to be a smaller one, or they can also be equal, but there's going to be a smaller one. And I can just say, okay, well, you're going to be the leftmost element of the merged list. And then I cross it off, okay? And then I say, okay, what's the smallest element now? Well, it's 3, so I'm going to write 3, and then I cross it off. And I continue this way, and because I'm always taking the smallest element, and I'm traversing sorted lists, I am guaranteed to obtain a merged sorted list. Okay, so it's a pretty simple example. So in this case, by the way, towards the end of this merge, I find 2 elements, both of them are 15. I can just pick whichever, it doesn't matter, right? It's okay to have duplicate elements. It will still be like a sorted list, right? So how expensive is merging 2 lists?
N time.
Yeah, it's linear, right? So it is linear in the sum of so I can say it is O of the size of SL plus the size of SR, right? And within our algorithm, since each one of them was of size n/2, we obtain something that is order of n, right? So kind of this part of the algorithm is order of n, right? So also want to just be precise and say how do we implement merge? I'll just write it. Take the smaller element from the 2 sorted lists, and then you repeat. Okay, when I take, I mean take out, right? So you're striking it out. Okay, so that's what merge is. And here we're using the fact that even though we have 2 lists, each of them of size n/2, each of them have already been sorted, so merging is pretty cheap. Okay. Okay, so let's talk about. Okay, before I move on, are there any questions about the correctness of this algorithm? What's why this algorithm makes sense? Right. This should make this is a it's pretty simple algorithm, right? To make sure we understand it, let's also analyze the running time, right? So the running time is going to be T of n 2 times, because we have 2 recursive calls. On what input size? Well, n/2, okay? And the additional cost, to split and to merge is linear, so O of n, all right? So you can either work this out, on paper, or you can just recall that we have proved the master theorem in recurrences, in which case A equals 2, right? Because let me use, that's 2, right? Then we have B equals 2, right? That's a part over there. And then D equals 1, that's because the exponent over there is 1, right? That's how we invoke the master theorem. And it will tell us, okay, we have to compute some magical ratio. The magical ratio is A divided by B to the D. In this case, it is 2 divided by 2 to the 1. It actually happens to equal 1. So we are in the so-called balanced case, where the work at each layer of the tree equals the recombination cost, okay? So this will tell us that the answer is n to the d log b n, which in our case is n log n, okay? So, so this is telling us that the algorithm merge sort that we have seen, it is an n log n time algorithm, okay? Now, this recursion sometimes is pretty magical. So another way to kind of sort of write recursive algorithm can be, think about it as an iterative algorithm. So let's do that so that, this is kind of probably the way you would implement it. So all the real work really is emerging, right? Because if you look up here, kind of in the non-base case, you just split, and at some point you get to the base case, and then all the recursive calls start coming back up, right? You start merging into bigger and bigger lists. There is nothing happening before you hit the bottom of the recursion. So one way to think about it is that you start a priority queue, okay? Or like last in, so first in, first out queue, and we populate it with all the single element lists, okay? So for example, let me use it a different color. Let's say that we have, within the list, we have elements 8, 3, 5, 9, and so on and so forth. We have, n of these things. These are the bottom-most sort of singleton lists, okay? And then as we start rising up in the first layer of recursion, we're gonna pop off from the queue, okay, the first two, and we're going to merge them. We're gonna say we pop off 8, we pop off 3. These are, by definition, these are sorted, right? This is like a single element list. That's another single element list. Now we want to merge them. So how are we gonna merge them? Well, we create a list of 2 elements and we put it at the back of the queue, okay? And now in the front of the queue, we're left, 5 and 9, right? So that's the first operation. Then, we pop off 5 and 9, and we create a sorted list of size 2. And we continue like this until we have processed all of the pairs of single element lists, okay? And, we have again at the front of the queue, the list 3, 8, and then 5, 9. This is, you can think about it as, one pass on our entire list where we went from n single element lists to n over 2 two-element lists. And each of those two-element lists is sorted. Can anybody tell me how expensive did this entire pass take? So I did, one operation, another operation, another operation. So here I'm sort of going over, right? So it's order of n, right? Because I'm doing n over 2 mergings, okay? So here the cost is order of n, okay? Now, so this is like one pass on the input. In the next pass on the input, what am I going to do? I'm going to merge these 2 element lists into one 4 element list. So that's the merging operation. I'm going to write 3, 5, 8, 9, right? And after I have merged all the 2 element lists into 4 element lists, I'm going to have all of them are going to be sorted lists of 4 elements each, okay? And how expensive is this second pass? Again, right, order of n, right? Okay, and how many passes do I have overall before I reach? I have log n passes. Okay, all we've done, if we just tried to visualize basically the recursion, the computation of this algorithm, and here it is, you can think about it as some tree like this, where we start with a single element list, we kind of merge them, and that's one pass, that's the second pass, that's the third pass, it's the fourth pass, there's log n passes, each of them cost n, right? And so there you have your balanced tree, okay? Anyways, we already knew it, what the answer was. This was just to kind of visualize the computation, to kind of feel how, how the algorithm is computing. All right. So that is merge sort. It's a pretty simple algorithm. Are there any questions about it?
Professor, so why is quicksort used in practice instead of like something like merge sort? Like they were both n log n, right?
Yeah, so I guess we'll get to that shortly, but briefly speaking, there are many sorting algorithms, also with different guarantees. Some of them are randomized, others are worst case. Some have a large memory footprint, others are not. Some are cache friendly, others are not cache friendly. Some are easily parallelizable, some are not. So all of these have like different trade-off, and there isn't one algorithm to rule them all. Okay, so there's usually it's like a toolkit of sorting algorithms, and depending on the type of data and the type of computing model, the size of your input, there's going to be different sorting algorithms that are sort of applicable. And it's not just about merge sort versus quick sort. There's also radix sort. There's also what's the other one called? Forget. But so bucket sort. So there's a bunch of things out there that bunch of algorithms out there that you can explore. We could spend an entire or multiple lectures on sorting algorithms. Today we're specifically talking about sorting because of divide and conquer and the next topic, which is about a lower bound. Okay, but so before we kind of get to the point, are there more questions about merge sort?
There seems to be a question about whether the iterative solution has a smaller space complexity.
Okay, if the question is, does the iterative solution have a smaller space complexity? Yeah, you can think about it as basically it's an in-place algorithm, right? So in the iterative solution, you're allocating basically a queue of n elements, and you keep just basically operating on this queue, right? And you have sort of an in-place algorithm, okay? The recursive algorithm, it depends, what are the costs of recursion inside your programming model, right? And it depends what kind of how you're charging for recursion, right? Whereas here, it's kind of pretty clear that so you kind of made you rewrote the algorithm to go up, and so there's no recursion anymore. There's just a state of the algorithm. It's iterative. All right. All right. So I just wanted to briefly touch upon a lower bound. So you can ask, can we do better than merge sort? Can we do better than n log n computation? And the answer is kind of both no and yes. Okay. So one no answer is that a merge sort falls under the umbrella of sorting algorithms that are known as comparison sorts. Okay. A comparison sort is an algorithm. Let me write it down. Let me use a different color. It is an algorithm in which the only operation performed on the inputs are comparisons. Okay, so when the algorithm picks up A1 and A2, it is not allowed, for example, to add them up or to divide them. It is only allowed to ask the question, which one is bigger? Okay, and then it will move on from there depending upon what the logic of the algorithm is. Okay, and we're going to prove a theorem that says that any comparison sorting algorithm, not just merge sort, but anything that only touches the inputs by way of comparison, must require big omega of n log n comparisons to sort lists of n elements. Okay, so that we learn that a merge sort is optimal among comparison sorts. Okay, so So we'll prove the theorem in the next slide, but just to make sure that it's clear what the theorem says. It says, look at a particular class of algorithms that have some restriction in the way that they're designed. They have their hands tied in the sense that the only way they can operate on the inputs is comparing things. Notice merge sort is one such algorithm, because how does it treat the inputs? Well, okay, we're recursing here, recursing, and then the only way we're touching inputs over here is to say, well, let's merge lists. But how do we merge lists? We're just comparing numbers. We're not saying to decide what goes here, we add up 3 and 2. We're just saying, which one is bigger between 3 and 2? Well, 2 is smaller, so we put 2 here, and then we cannot cross it out, okay? So merge sort is clearly a comparison, is clearly a comparison sorting algorithm. And we're saying that within the class of sorting algorithms, it is not possible to do better than n log n comparisons, okay? Now, at the same time, okay, that is just a class of algorithms. There are sorting algorithms that are not solely based on comparisons, okay? For example, suppose that the elements are W bits long. Think about this as the word size, okay? So that's W denotes the word size. Then an algorithm that we are not seeing in this course, but you may have seen in other courses, radix sort, uses W times N bit operations, okay? Elementary operations on bits. And if you think about it, merge sort actually costs more than that, because a comparison requires you to look at all of the bits, right? If you're comparing 2 integers of W bits each, then to perform a comparison, that's going to cost you order of W bit operations, right? Because you have to say, okay, you start from the most significant bit, you see if one of them is bigger, is 1, the other one is 0, then you already know the answer. If they're both equal to 1 or both equal to 0, then you have to move to the next one. And you may have to scan the entire integer to decide which one is bigger, okay? So in this case, compared to radix sort, merge sort is log n more expensive when you start computing as bit operations, okay? And this was related to the question that was asked earlier, why does anybody care about merge sort? Well, first, that's a pretty nice simple algorithm, but it works well with certain data structures. For example, it works extremely well on linked lists. Also, it really depends, where does your data sit? Do you want to parallelize things, and so on and so forth. So generally, sort of libraries will offer multiple sorting algorithms nonetheless, okay? But the point that I wanted to make here is that there are sorting algorithms that are not covered by this theorem because they do other things, okay? In particular, radix sort will do operations based on the bit representation of the inputs that are not just comparisons. All right? Okay, so this was just to put this theorem in perspective. That was the point of this slide. But now we want to prove this theorem, okay? So that's what we're going to do next. Let me see, are there any sort of open questions? Or I see there's already some answers there. Okay, so then let's move on. We want to prove that any comparison sorting algorithm requires n log n comparisons to sort a list of n elements, okay? This is the first, let's call it a formal negative result that we see in this course. It's not about designing algorithms, it's about proving a limitation on an algorithm. So, to look a little bit different. So here we are. So we want to prove that, any comparison sorting algorithm, has some limitation. Okay, so fix such an algorithm. Let's call it A. So here we have it. It's a comparison sorting algorithm, okay? Now, without loss of generality, let's focus on input lists, A1 through N, where the elements are distinct. Why? Well, I can do that, right? This algorithm is supposed to work on every single input. In particular, it has to be correct on input lists where all the elements are distinct, okay? All right. Now, notice that when A is computing on the input A1 through N, it is implicitly computing a permutation on these N elements. Why? Because its output its output, let's write it down, is going to be something that looks like a pi 1, a pi 2, and so on and so forth, up to a pi n. What is this pi? It is the pi that creates the sorted list, right? Right? So when A is computing a 1 through n, it will output, the sorted list, and that sorting relative to the input will define a permutation, because each of the elements will be somewhere in the output. So if one, if the first pi of 1 here will say which of these n elements appears in the first location, pi of 2 will say which of these n elements appears in the second location. It cannot be the same one, must be at some other one, right? It's not like you ask me to sort 10 elements, I throw away half of them, and I repeat twice the other 5, and I write them in sorted order. Like, all of them must be in the output. Okay. Moreover, not only is there a permutation for every input, but all permutations are possible outputs, right? Because I can write down inputs to create whatever permutation I want, right? Because among all the inputs, for example, I could write the input 1, 2, 3 up to n. I could write n minus n and minus 1 and minus 2 up to 1. I can permute any of these things, and so sorting them will kind of create the effect of any permutation. Okay, so this algorithm, at the end of the day, because it's correct on every possible inputs on distinct elements, it will implicitly compute a particular permutation. Across all inputs, it's going to have to compute all permutations. Okay. Now, let's focus on some abstract quantity, a set S, that will denote the possible permutations at a certain point in time in the algorithm, right? So you can imagine the algorithm with press play, and before the algorithm starts, the possible permutations could be anything, right? The algorithm hasn't done any work. And as it does more and more comparisons to discover things about the input, the set of possible permutations that will be defined by the output will get smaller and smaller until it gets to the permutation that describes the output. Okay? So in other words, before the algorithm starts, the cardinality of S is the cardinality of the set of all possible permutations, which is n factorial, right? Now, at each comparison, depending upon what happens, this set may change, okay? So let's kind of look at a picture like this. Here's this set of possible permutations. The algorithm does a comparison. Let's say it says, I would like to compare AI and AJ. And the algorithm will ask, is AI less than AJ? And the answer is a yes or no, right? And depending upon the answer, it will either do one comparison or some other comparison. Maybe they're the same, maybe they're not. It's the algorithm's business which comparisons it wants to do next as a function of the answer to this question, right? But depending upon what the algorithm does, there is going to be some new set S1 and new set S2, which are all the possible permutations that are consistent with this computation path. And similarly here. Okay? Because by the time the algorithm has finished computing at the last comparison, this set S must be a singleton, the permutation that defines the output. Okay? So here, in one case, S goes to some S1. S, in the other case, S goes to some other S2. Okay? Maybe they overlap, maybe they don't. It's not our business. But we do know that because all permutations are possible outputs, the union of S1 and S2 must be S. Okay? And therefore, because the union is S, then I know that at least one of them is large. Right? Because if I have any two sets, S1 and S2, whose union is S, they cannot both be small. At least one of them must be half the size of the original one, right? If they were both small, then there's no chance they could ever cover the original set, okay? So this tells us that a comparison divides the possible permutations by at most 2. In other words, a comparison, you can think about it that when you ask a comparison, you learn a bit, 1 bit of information. And it cannot be that with this 1 bit of information, you're suddenly able to realize, aha, out of all the possible permutations, now I have, I don't know, I can divide them by 100 and still be correct. I can't do that, right? So I learned 1 bit of information. So you'd expect, in the best case, my set of possible permutations halves, okay? So it cannot go down too fast, all right? Now, for the algorithm to finish its computation and have a correct answer, it has to reduce the size of S, reduce the size of S, reduce the size of S many times until the size of S is 1, all right? But now we know that reducing the size of S cannot be too fast. You want to reduce it a lot, you need a lot of comparisons, all right? So the computation we want to do is to say, well, the number of comparisons until the size of S is 1 is going to be at least log base 2 of n factorial, because n factorial is the number of permutations we start from. In the best case scenario, we halve it each time. The number of halvings of n factorial to get 1 is log base 2 of n factorial, okay? Now, n factorial is it's a bit of an ugly expression, but you may be familiar with the lower bound of it, which n factorial is always at least n divided by e, everything to the n, okay? Now, what is that? That is n log n minus n log e. Now, presumably at this point, you're pretty familiar with sort of growth, asymptotic growth. This is a low order term. The dominant term is n log n, okay? So this whole thing here is big omega of n log n, which is what we wanted to show, right? We wanted to lower bound the number of comparisons of a correct algorithm. And here we're saying that the number of comparisons must be at least big omega of n log n. Now, this lower bound is just a worst case lower bound. What does it mean? It means that we have shown that there must be at least 1 leaf in this tree of comparisons that is who is at depth big omega of n log n. In fact, a more sophisticated argument can prove that on average, the average depth of a leaf in this tree is also omega n log n. Okay, so it's not just there is one placed on some input that you're going to pay n log n, but on most inputs you're going to pay for depth of n log n. Okay. All right. So let me just zoom back out a little bit. Yeah.
So shouldn't the number of comparisons be less than or equal to log n factorial? Because n factorial is the number of leaves. And you can have, if you have a comparison at each layer and your depth is going to be less than or equal to log of n factorial. So shouldn't the comparison be less than?
No, I cannot hope to show that the number of comparisons is at most n log n, because you can have stupid algorithms that like to make comparisons for no reason. And what about them? Oh. So what I want to show instead is that every correct algorithm, whether it is stupid or intelligent, they all have to pay at least n log n, okay? So I'm trying to prove a lower bound on how many comparisons it is, this algorithm must make. An upper bound I cannot say, right? You can have correct algorithms that are just very inefficient in their use of comparisons. So that like, but these are good sanity checks, right? When you're trying to kind of prove something that is supposed to hold for all algorithms, you should check whether it also holds for some concrete algorithms that you can think about, right? But yeah, no, here I definitely mean at least. Okay.
I see. Thank you.
Now, regarding how do you go from n factorial to n over e to the n? Well, these are things that so this is combinatorial stuff that you may have seen maybe in CS70. We're not going to go over it. It's just hopefully it is reasonably intuitive why n factorial has something to do with n to the n, right? It's not quite n to the n, it's slightly less than that, right? Because n factorial is n times n minus 1 times n minus 2 and so on and so forth. But you should see some n to the n there, right? Because by the time you've gotten to n over 2, you already have basically n things of order n. So you have something n to the n, right? And the correct lower bound, or at least a good convenient lower bound, is to divide by e to the n. Okay. So this is just some combinatorial fact that has nothing to do with algorithms. It's just something that you can look out and check for yourself. All right, so let me just check here what questions remain open. And maybe the moderators can help me with.
There seems to be some questions about the subscripts in the yes and no box and what they represent.
Right, let's kind of go over what this picture means. So you can view the computation of a comparison sort algorithm as a tree, right? So you press play, it will start doing something, right? The only thing it's allowed to do is do comparisons. So the first thing it will do, it will pick up 2 elements and compare them, okay? So let's say it just started. So S is all possible permutations, and it decides specifically to pick up AI and AJ and compare them. Now, depending on the answer, he may do a different comparison. Or at least I hope it does a different comparison. It might be stupid algorithm that say they compare AI and AJ, they get an answer and they ignore it and they do some other the same comparison regardless, right? So, but it will do something. It doesn't really matter what. We can just call it AI prime and AJ prime and AI double prime and AJ double prime. We don't really care what these are. I'm just trying to tell you that there's going to be a subtree here, another subtree here. And somehow at the end of the subtrees, at the leaves, there are going to be, for every possible input, there's going to be a correct permutation at the end. So somehow this set S of all permutations has to keep being reduced in every possible path until you reach a leaf, and it must have size 1, because that is the only way that it will have computed the correct permutation, okay? So the subscripts here are not they're not really mean anything. It's just like some notation to say something arbitrary. And these things here are just saying, well, there are some permutations here, some other permutations here. In the best case scenario, this is a perfect split of S into some S1 and some S2, but maybe not. Maybe you just have some overlap between the two. And ideally, a good algorithm should aim for always splitting S, okay? You get like learn one bit of information and that splits S in some fashion, okay? All right, more questions. There's one question about worst case. So worst case here specifically means, yeah, this basically, right? So all we have shown in this proof is that there exists an input that will cause the algorithm to make order of n log n comparisons. And you might say, well, who cares? Like maybe for all other inputs, it makes 5 comparisons, which is pretty good for me, right? So a stronger statement would be to say on most inputs, okay? But that's not the proof that we're showing here, okay?
Sorry, I just have a quick question concerning the boxes. So basically, like after you do the comparison on AI and AJ, for example, if the answer is no, so like by throwing out, like we could essentially say that we're not going to consider any of the permutations where AJ is greater than I. For example, if like or any of the permutations where 3 comes before 2. Is that the basic idea?
But that would be a smart algorithm, right? But some algorithm may choose to, I don't know, not do that. But it just makes our proof better, right? So I mean, it just helps us, okay? But a smart algorithm might indeed do that, right? So that's why kind of S changes to S1 and S2, right?
Mm-hmm.
And again, S1 and S2 may overlap, but we don't use it in the proof. All we really care about is that whatever, like every single permutation here must appear in S1 or S2 or in both, right? Because S1 or S2 cover everything. And just because they cover everything, then we know that at least one of them must be large. Okay?
Yeah, makes sense. Thank you.
Yeah. There's a question about whether we prove some algorithm. No, here we're saying every algorithm, every comparison sorting algorithm requires n log n. Proving negative results for some algorithms is very easy, right? You just say, does there exist an algorithm that is very inefficient? Sure, here's one. I write down an inefficient algorithm. What we want to prove is that every algorithm must be, somewhat inefficient, okay? And merge sort shows that there exists an algorithm that actually can match this lower bound, that indeed it must have paid to n log n and only has to pay n log n. Okay. There's some questions about S1 and S2. Do they overlap or not? It doesn't matter whether they overlap or not. They may overlap, but all that matters is that as a union, they are like they cover the set we started from. All right, so I'll just maybe take one more question about this one. I'll just spell out again, why we're looking about all these permutations. Let's say that your input is, I don't know, 3 to 1, okay? So a sorting algorithm must output 1, 2, 3, okay? So it has computed a permutation. What is that permutation? It says pi of 1 equals pi of 2 equals, and pi of 3 equals, right? So pi of 1 in this case is 3, right? Because at location a pi 1, we find what was a3, right? So pi of 2 is 2, and pi of 3 is 1, right? And there is one and only one permutation that describes this output, okay? And in general, I can just move around 1, 2, 3 in whichever of the 3 factorial ways, and each of these 3 factorial ways are going to define one out of those 3 factorial permutations. They're in one-to-one correspondence. All right. So I think maybe, let me see if there's any other big questions. Pi is a permutation. There's a question there. All right, so that's as much as we're going to talk about sorting today. So now we're going to talk about median finding. So it's another operation on list, okay, on lists. Again, not arithmetic, just some other operation on lists, also unrelated to sorting, by the way. Let's just make sure that we agree on what we're trying to do. We're again given a list of numbers, okay? And what we want to output is one of the inputs, so I mean one of those numbers from the list, such that half of the numbers are smaller and other half is bigger, okay? So just to make sure it's clear, let's compare the mean from the average, okay? Which is when you sum up all the numbers and divide by n. For this first list here, can anybody tell me what is the average and what is the mean?
Median, right? Not mean?
Oopsie. Yes. I wish I had search and replace. All right, so let me just do it in a very crude way. I'll just make the AN into a D. Med for median. At least I got the title right. Okay. Okay, well, at least okay, maybe it wasn't as end this part here. Sorry about that. Mean is average, but median is something different. So can anybody tell me for the first list, what is the average and what is the median? 1 and 1. Okay, great. Thank you. 1 and 1. All right. So that was easy. Let's do the same thing for the next one. For the second list, what is the average and what is the median? Right, 4 and 1, right? Because here I have 12 divided by 3, that is 4, right? And over here I still have 1. Okay. How about the next list? $34 and 1, excellent. Why? Because we have a 102 divided by 3, that's 34, right? And here I still have 1. And you see the pattern, right? So this is 1002 divided by 3 is 334, and this is still 1. And this is just to tell you that median and average are different things, okay? And some features are that the median is always one of the elements in the list, and it is kind of less sensitive to outliers, as we've seen here, okay? Doesn't mean one is better than the other, it just means they're different things, and depending upon whatever statistics you're trying to compute on data, you may want to use one or the other, okay? Now notice that the average, it is an arithmetic computation, right? That you can compute, but how are we going to compute the median, okay? So that's like less about arithmetic and more about kind of comparing elements, right? How about, can anybody mention a quick and dirty way to figure out the median?
Sort and then find the middle. If it's
Great.
odd.
Yes, exactly. So we can sort the list, sort, and take the middle element, right? And yeah, I'll just mention it. When it's an odd number of elements, then there is a middle. When it's an even number of elements, there is no middle. You need some convention for that. It doesn't really matter what it is. You can take the lower one, the higher one. Some definitions consider averaging the two middles, whatever. It doesn't really matter. Like, it's kind of not very important for here for now. The main point is that this is going to cost you n log n comparisons. Okay, and that's respectable. Okay. It is respectable, but we should ask always, can we do better? Okay, and can anybody suggest why there is a high-level intuitive reason that may point to the fact that we can do better?
We don't need to sort the entire list to find the median because you can just find the first half elements.
Yeah, like intuitively sorting gives me a lot of information. It gives me who's the first element, who's the second element, the third element, and I did all that work. Well, all I cared about was what is the middle element had I sorted it. But I don't, like above and below, I don't care what happens there, right? I just need to know that there is half of the elements that are below in whatever order, and half of the elements are above in whatever order. I don't care about making the effort to extract this precise order between them, okay? So intuitively, it feels like a simpler problem. Therefore, we may expect to do better than n log n, okay? And that is precisely what we're trying to do, we're going to try to do, okay? So I'll just write here, the idea here is like we do not care about the order of elements above and below. Oopsie. The median, right? We just don't care. Okay, well, this is a lecture about divide and conquer, and we will see a divide and conquer way to do that. In fact, we'll solve a slightly more general problem called selection, where not only it's not just the median, we're gonna look at, we're gonna find the kth smallest element, okay? And in particular, the median is just when you set k to be n over 2. Okay? And you might wonder, okay, wait a second, like, why are we trying to kind of make our problem harder? Well, this is, you can think about it, this is kind of analogous to how strong induction sometimes simplifies recursion, okay? Like if you try to solve a harder problem, it means that when you recurse on yourself, you may have more flexibility, okay? So it doesn't mean always, like doesn't mean that, every time you're faced with an algorithmic problem, you should think, I'll just make it harder and then solve it. That's not how it works. Just sometimes, when you're doing recursion, it may help to think of a kind of more flexible API that you're solving, so that when you do recursive calls, you can actually, they offer more flexibility, and maybe in the end, it ends up being sort of easier to solve. Okay, so that is what we're going to do. We're going to now try to design an algorithm, divide and conquer algorithm for the selection problem. Okay, so that's our goal for now, and I hope it's clear that as a special case, when you set k to be n over 2, you will recover an algorithm for the median. Okay, great. I don't see any more questions. It means like everything is clear. All right. So now the high-level idea is going to be that we're going to have some way to pick an element from the list, and then we're going to split the rest of the list to be below that element, above that element, or equal to the element. So let's call these S left, SA for the element A, and SR. S left is that the elements in S that are smaller than A. SA are the elements in S equal to A. There may be more than one, right? And SR is the elements in S greater than A. And then we're going to recurse in a straightforward way. We're going to pick A somehow. We'll talk about somehow in a moment. We're going to compute these lists. By the way, how expensive is it for me to give an A to figure out these 3 lists? Linear, right? Because I just scan, right? I have A in my hand. I have a list in front of me. I just go through from left to right, and I throw things in 3 buckets depending upon the outcome of the comparison. Okay, so this we can split in linear time, or more precisely, a linear number of comparisons. Okay, and now we have various cases for the recursion. Let's say that the index that I'm trying to select happens to be less, or at least at most, the number of elements that ended up less than A. What should I recurse on here? What should I recurse on here? Right, many people say SL, and I remind you that we have a 2-input algorithm, so it is SL and K, right? Because why is that? Look, we wanted to figure out what was the kth smallest element from our list. We took somehow an element A, and we figured out that all these SL elements are definitely smaller than A. And there's at least K of them. So I can safely ignore the rest of the list. I just don't care what's going to happen there. I can still select the kth element from this smaller list, right? Okay. All right, so here's another case. Suppose that the index K that I want to select is strictly greater than the number of elements sitting below A, but it is no more than the number of elements that below A and equal to A. Then what should I return here? What should I return here? Is it a recursive call even? I should just return A, right? I could return SA, but SA is just A, right? I just return A. This is just telling us that K has landed in the middle of A's, Okay, so here I return just the element A. Okay. Now, in the other case, it could be that the index K is pretty large. In particular, it wants to select something that sits to the right of all the elements below A and all the elements equal to A. In this case, what should I recurse on? So here's half tricky, right? Because I do want to write SR here, but I have to adjust the index, right? I have to shift the index to be relative to the size of SR. So I'm going to write K minus size of SL minus size of SA, right? Because K was relative to the big list, okay? But now I have, all these things are definitely smaller, okay? In which case I'm shifting back my index, okay? All right. So that's a pretty, divide and conquer is very powerful, right? Like imagine kind of writing this algorithm kind of raw without any recursion. That would be like pretty annoying. But here it's like fairly elegant, right? It's kind of the correctness is kind of very clear. And now we're going to analyze the running time, but sort of the ability to use recursion to kind of split up your problem into smaller chunks, so that then you're kind of recursively solving it until it becomes trivial, right? It's a very powerful technique. All right. So now we should talk about the running time of this algorithm, okay? Which is, notice that not entirely clear, right? Because we haven't specified yet. We haven't specified yet how we pick A, right? So in some sense, right now, the algorithm is slightly underspecified. There is one operation we haven't said how it is done, right? But nonetheless, let's try to understand, how should we pick A? Well, the recursion here means that we go from list size S to list size that is the maximum of SL or SR, right? Because look, I don't know a priori which of the two branches I'm going to go into, okay? So in the worst case, it could be one or the other, whichever is larger, right? So I go from list size S to list size maximum of SL and SR. But the sizes of SL and SR depend on how A was picked, right? And there are some pretty unlucky choices of A. For example, a bad case would be that if A is always, let's say, the largest or the smallest element of the current set, because kind of pictorially, we would have a list. And if my A is this one, then my SL is going to be this one. That is going to be SA. And I'm going to have an empty SR, right? And what if the next A is this one? Then my new SL is going to be this one. And I'm just going down by 1, 1, 1, 1, 1. So I would be paying order of n plus order of n minus 1 plus order of n minus 2, ... right? And this is all order of, it's order of n squared, which sucks, right? So there are choices of A that are not very helpful, okay? It's not just, I made the problem smaller and therefore my algorithm is fast. I need to make the problem sufficiently smaller so that I'm not, having too much work, right? Now, what would be nice is that A splits S roughly in half, right? Because we're paying only for the maximum. And the best thing would be for us to split it roughly in half. In such a case, we would get a recurrence, which is something like T of n equals to what? Let's say for a moment that A is splitting always things in half. What recurrence would I get? T of n equals what?
2 T of n over 2.
Is it 2 here? Remember that I'm recursing in only one branch, right? Just one. So it's not 2, it's 1. And then yes, times T to n over 2. And then plus, what is the recombination cost or the splitting cost? Order of n, right? Great. So this recurrence, if we had it, it would work out to be what? I mean, it's a geometric series, right? It's like n plus n over 2 plus n over 4 and blah, 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 right? So all of this converges to order of n. Great. So which would be nice, right? So before, through sorting, we had an n log n algorithm. Now we have, no, we don't have yet, but if we knew how to pick A well, to split this list size into halves, we would obtain a linear time algorithm, or at least an algorithm that runs with a linear number of comparisons. Okay. However, picking A in the middle, it's kind of the problem we wanted to solve to begin with. It was basically finding the median. Okay. So that's kind of annoying, right? So it feels like a good choice of A requires us to solve the problem that we wanted to solve through this algorithm. Okay, it seems like we're kind of stuck. Okay, but before we move on and fix this, is it clear, what is a bad choice of A and what is a good choice of A? And then why this good choice of A is kind of inconvenient because it's this problem that we wanted to solve. Great. But I see here there's a question about why is there combination cost order of n? Well, this order of n here is this part over here, right? So when we are given A, we need to write down SL, SA, and SR. And that's a linear number. It's a linear number of comparisons. So when we put this cost over here, it's not just the recombination cost. It's just whatever is happening beyond the recursion. In the algorithms that we have seen so far, the cost was primarily after the recursive call. In this case, the cost is coming before the recursive call. In general, again, I know I have called it regularly recombination cost, but really we should call it more splitting and recombination cost, right? It's just whatever is happening beyond the recursion, because we have to account for all the time here. Some of the time is in the recursion, and then you have to write the rest of the cost somewhere, right? All right, there's a question about explaining the bad case again. If my A happens to be, for example, all the way to the right of, imagine that I'm writing pictorially the list sorted, just to visualize it. And I'm picking A just because I'm unlucky all the way to the right. It means that my next SL is going to be made up of n-1 elements. And if I keep doing that because I'm just like really unlucky, I will go from n to n-1 to n-2, and I will pay linear cost to split, linear cost to split, linear cost to split. So that's order of n, order of n-1, order of n-2. I add them all up, that's n squared, and n squared sucks. Okay. All right. Great, or at least not great, because we don't have an algorithm yet. But what we're going to see now is a pretty simple way to fix this, which is we're just going to kind of cheat, and we're going to start using randomness. I'm going to change, rather than getting an algorithm that runs in a sort of a doesn't use randomness, like it's always correct regardless of randomness, right? I mean, it will be always correct, but the running time will be like a random variable. Okay, so we're going to pick A at random. Okay, now you might wonder, wait a second, like if I pick A at random, the probability that it lands specifically in the middle of the sorted list, it's pretty small. Yeah, I understand, but we're going to relax this condition. We're going to call A to be good if A is between a 25th and a 75th percentiles. And 25 and 75 are arbitrary constants. You could just pick, I don't know, a 10th and 9/10, doesn't matter. The point is that we're going to let A be good as long as it lands into, say, the middle half, okay, of the sorted list. Now, we don't have the sorted list, but we can still define A to be good if so, right? All right, and when A is good, the new set shrinks by a constant factor. Can anybody tell me, if A is good, then by what can I upper bound both SL and SR? 3/4, right? 3/4 times size of S, right? Because if in the two worst cases are when A ends up on this side or on this side, right? And depending upon where K is relative to that, we may recurse on one or the other, right? So it may not shrink by half, but it goes from S to 3/4 F. That's still pretty good, okay? Moreover, because we relaxed our notion of good to be anything in the middle half, can anybody tell me what is the probability that A is good? It's a half, right? Because, I mean, it's like, it's here, right? So anytime it lands in this middle half, we call it good. It's a middle half, so that's like half of the A's, right? So also notice that if I have an A, I can check whether it is good or not, right? I pick A at random, and then I wonder, I wonder whether A is good. Well, I can just go and check that, right? That's like a linear number of comparisons, all right? So in expectation, how many tries does it take me to get a good A? 2, right? And again, I can write here because I know when to stop, right? If I didn't know whether A is good, like I may not get like a good recursion, okay? But here I'm gonna pick A at random, and then after that, I will check if A is good. I may be unlucky, so I'll try again, but you know, each time I sample A, I have a pretty good chance that it will be good, half, right? So in expectation, it's gonna take me 2 tries to get a good A. All right. So now, with this information and having specified the algorithm, having told the algorithm, please pick A at random, now we're going to have a new guarantee on the running time. First and foremost, we are not going to compute the running time itself because the running time is going to be a random variable. Instead, we're going to compute the expected running time. Okay. Now, the expected running time is going to be the expected running time on a recursive call. What should I put here? What is the input size, right? So it's 3/4 n, right? Plus, I have the linear amount of cost times the number of tries, number of times to find a good A, right? So sort of, let's say, number of tries to get good A, right? And you know, for each of these tries, I'm going to pay order of n to figure out whether it's good, plus order of n in case it is good to split the list into the 3 parts, right? All right, so that's good. And we just do the computation, okay? So I just rewrite this. This is, you know, expected time of 3/4 times n plus 2 times order of n, okay? Great. So again, expected time, 3/4 of n plus order of n because the 2 goes inside. And this recursion resolves to what? What does the recursion resolve to? It's just order of n, right? Because like you can think about it, you know, one way to you have, you know, order of 3/4 times n plus order of 3/4 squared times n plus order of 3/4 cubed times n, right? All of this is kind of sum of 3/4 to the I, right? Times order of n, right? But that's just order of 1 times order of n, right? Because that's a geometric series of something smaller than 1. Okay, it will converge to a constant.
Question, should we say the expected value of T of n is less than or equal to the cost at 3/4? Because that's the worst case.
Sorry, you want to say, sorry, the expected time of T of n?
Yeah, is that less than or equal to the expected value
yes.
of T of 3/4?
Yes, there you go. Thank you.
Okay.
Yeah, thank you. Yeah, please.
There is a expected value of number of tries to get good A.
Yeah.
So you unrolled 2 recursions in order to put that in there?
I didn't enroll 2 recursions because when I sample A and I haven't recursed yet. Before I recurse, I want to make sure my A is good.
Yes.
And I can check that, right? Because all I need to do is I need to make sure that if I compare A against all the other elements, it will have at least 25% of them below and at least 75% of them above.
So if you get a bad A, you try one more time.
Exactly.
Oh, and then you recurse.
And then I recurse, exactly. And then when I recurse, then I go back and I compare again. I create the 3 buckets with respect to A, right? These 3 guys, right? And then I recurse. Okay, so I only recurse when I have a good A, which ensures that my problem size goes down, by a constant factor.
Okay.
Now, it's important here to point out that, even though we're using randomness, it doesn't mean we're making mistakes. It just means that our algorithm has a runtime that is a random variable whose expected value is order of n, okay? But it is still the case that on every possible input S and on every, index that we're selecting K, we return the correct answer, okay? And it's just the number of steps is linear, okay? The number of comparisons and expectation is linear. All right, so whenever you use randomness in algorithms, it could be for various reasons. It could be that it affects your running time or maybe even your correctness. And we'll see some of that later in this course. In this case, it's not about correctness. We're always correct. Okay, it's just about when we halt.
Excuse me.
Yeah.
I do understand how the recurrence relation for the running time comes from and why it makes sense, but I'm not exactly convinced why the expected running time, why does this hold for the expected running time?
So I didn't understand. Why are we studying expected running time, or?
No, why does this hold for the expected running time?
This part over here?
Yes.
Okay, good. Now, first, let's remember that expectation is linear, okay? So let's maybe write first like a bit, let me make some space here. I'm gonna cancel this thing, okay? And so we can first write T of n. Now, T of n at this point is a random variable, right? And what is it equal to? Well, it will equal to, it's not really, I mean, it's not really the same random variable, but it's another random variable that represents, the recursive call, right? Plus a kind of the number of tries, right? Times order of n. Now, this is a random variable, that is a random variable, right? And, it's a random variable, so, it doesn't have like a specific value, right? We can ask questions about a distribution. We can compute the variance, we compute the expectation, we can compute with what probability it is higher than a certain value, and so on and so forth. So all we're doing is to say, well, you know what? I'll just apply the expectation operator to all of these things, so I get some clean answer, okay? That's all. I'm just saying, I have random variables, let's just look at their expectation. Why? Because I want to study the expectation. We could have asked a different question. We could have asked, I don't know, what is the probability with which this random variable is linear? We could have asked that question, right? But we're specifically trying to ask a simple question, and we're just saying, look, there's a random variable, let's just ask its expectation and make sure it's linear, okay? It doesn't tell us that it doesn't tell us necessarily it's like a very nice distribution, right? Because you can have, maybe sometimes it's very large, sometimes very small, but it's a positive number anyways, so it cannot, be super crazy. Hopefully that clarifies.
Yeah, thank you.
Also, reading from the chat, how do you know when we pick a bad A? Like, how do you know A is bad if it is bad?
So again, when I pick A, I'm going to check. So let's say that I pick A, right? And A is sampled from S. And then I can compute S kind of less than or equal, right? And S greater than or equal, or let's call it, okay, let's just for a moment, it's just easier to think for a moment that A is unique inside the list. So let's think about it first like that. We compute S less than and S greater than, right? And I want both of these things to be of size at least S over 4. Why? Because it will guarantee me that I have at least as many elements here and at least as many elements here, which forces A to be somewhere in the middle here. Okay? So when I have a specific A in mind and I'm wondering, is it between the 25th and the 75th percentile? I can just count the number of elements less and greater than. And if there is at least S over 4 elements less than it, and at least S over 4 elements greater than it, then it must be somewhere in the middle, right? In the middle half. And if it's not, then I'll just try again. And I know that by definition of good, I must, in expectation, will take 2 trials to do so.
Okay, thank you.
Again, this is important to check it. Like if you couldn't check it, then we wouldn't be able to write this recurrence relation. Okay, so before I maybe stick around to ask more questions, I wanted to say that this is as much as I wanted to say for today. The next lecture, we're going to cover a very fun topic. It's called the fast Fourier transform. You can check from prior semesters, it is the most beloved topic by every student. It may be useful to read up on the FFT before the lecture, just so that, maybe things will make more sense rather than starting from scratch. It will be in particular useful to remind yourself what are roots of unity and what are polynomials. And we'll be using both of them to talk about the fast Fourier transform next time. And just in case, yes, I was being sarcastic. It is a very cool algorithm, and it is beloved, maybe not by every student. Yeah, so that's as much as I have for today's lecture. I'll stick around for more questions. Okay.
Thanks, Professor.
Have a good day, everyone.
Thank you.
Looks like we've got one hand raised.
All right, so maybe in the meantime, we can stop the recording. I don't know if I can do it from here. And
You can do it.